In this video, we're going to look at some AP-style practice questions on limits. Our first question here, we've got a graph, and the graph is of the function f of x is equal to 20 over 1 plus x squared. But the question is specifically telling us it's shown in the standard viewing window from negative 10 to 10 on the x-axis and negative 10 to 10 on the y-axis. And we're asked to evaluate the limit as x goes to 0 of f of x. This is a little bit of a tricky question. If you look at the graph as x is approaching 0, it looks like we have a vertical asymptote here, and that our function is going to infinity on both sides. And so answer A here, infinity, it is tempting. But let's remember, whenever we have a limit as x approaches a number like 0, we should plug it in and see what happens. So if I plug in 0 to my function, 20 over 1 plus 0 squared, look what happens. We get 20 over 1, or just 20. I actually have a limit of 20 as x is approaching 0. There really isn't a vertical asymptote here. What's happening is that as this graph continues on up, and I'm going to go into my title here, it actually turns around and comes back down. We have no vertical asymptote because notice our denominator is 1 plus x squared. If I'm going to get a vertical asymptote, that usually happens when my denominator is equal to 0. And 1 plus x squared, there's no way that that's going to equal 0, because if I square a number x, the result has to be a positive value or 0, and then I'm adding 1 to that, and so my denominator is always going to be a positive value. Therefore, we have no vertical asymptote. The limit cannot be infinity. It is in fact 20. Question 11 gives us this piecewise function, and it says for what constant k is this function continuous at x equals 2? So we're trying to find a value here that makes this continuous. Now notice in the first piece of my piecewise function, I've got a rational function here. My denominator is x minus 2. And so obviously if I substitute 2 in for that x, my denominator would be 0 and the function would have no value and therefore could not be continuous. But what this question is indicating to us is that there's probably just a hole there at x equals 2, and I could fill in that hole with a value. We have a removable discontinuity here at x equals 2. So I'm going to rewrite my function here. We're going to have to factor to figure out if I've got a hole. And really what we're doing here is looking for the limit. I'm going to kind of rewrite our question here. What I really want to know is what is the limit as x approaches 2 of this rational function. There on the top, I'm going to factor out an x. Every term has an x. So I'm going to factor it out, and I get x squared minus 6x plus 8 over x minus 2. And let's continue factoring. Whoops, I'm not going to have room to do that there. Let's move down. Sorry about that. Move down to the next row. Limit as x approaches 2 of x times, and we're going to have x and x. Numbers that multiply to give me 8 would be 4 and 2, and if I make them both negative, then I get that negative 6x in the middle over x minus 2. So notice now that I have it factored, my x minus 2's, they do indeed cancel out. And remember, that indicates that we've got a hole on our function. We have removable discontinuity on our function. We actually have a limit. And in order to find that limit, what I need to do is take 2 and plug it into the x's that are left. So if I plug in 2 here, I have 2 times 2 minus 4 over 1. Since everything canceled out in the denominator, it would be 1. And so in the numerator, 2 minus 4 is negative 2 times 2 would be negative 4. And so answer B, that is our correct answer. My limit is negative 4, which means the hole is occurring at 2, negative 4. The coordinates of the hole are 2, negative 4. And so if I assign the value of -4 to k, then I've created a continuous function. Now, question number 12, I will admit that this is probably one of the more algebra-intensive questions here, and probably harder than anything you're going to see on the limits test in my class. But let's look at this question anyway. The question is asking, what's the limit as x goes to infinity? And the challenge here is that I've got a square root of x squared, and then we're subtracting x here on the end. And so if I just had a square root function, or if I just had a linear function, then I could figure out what the end behavior was, what x is doing at infinity. But since we're mixing the two, that's causing a little bit of a problem. If I'm looking for a limit for a horizontal asymptote, typically those happen on rational functions. And so one strategy for me here is to turn this into a rational function by multiplying by a special value of 1, like multiplying something times the numerator and the denominator, multiplying the same thing in the numerator and the denominator. And so here's what I'm going to do. Here's the strategy. We're going to take square root of x squared plus 8x minus x, and I'm just going to put that over 1 to make it look like a fraction, because I'm trying to turn this into a rational expression so that I can look for a horizontal asymptote. If we're looking for a limit as x goes to infinity, that means we're looking for a horizontal asymptote. So I'm going to multiply by the square root of x squared plus 8x, but instead of minus x, I'm going to do plus x. What I'm doing here by choosing that expression to multiply by is that I'm kind of creating a difference of two squares scenario, and that's going to help me get rid of this radical. But if I multiply by this on the top, I have to do the same thing in the denominator. And so now I'm just multiplying by 1. I'm not changing the value of what I have. I'm just changing the way it looks. Now let's think about what I've done here. If I relabel my first expression here as a minus b, and then I'm multiplying that times a plus b. Notice my expressions are the same except for the sign in the middle. Well, we know that a minus b times a plus b is equal to a squared minus b squared. So what's going to happen when I multiply these two expressions is I'm going to end up with a squared, which is the square root of x squared plus 8x squared minus b squared, or in our case, x squared, over, and then we still have this same expression in the denominator. So now in my numerator, the squared kind of undoes the square root, and I'm left with x squared plus 8x minus x squared on the top, and then on the bottom I still have this same expression. So that was the tricky part to this question. Now we're down to an expression that we've kind of worked with before in class. Let me do one more step of simplification. On the numerator I've got x squared minus x squared. Those are going to cancel out, and I'm just left with 8x over the square root of x squared plus 8x plus x. Alright, so I'm going to erase some of my work up here at the top. And remember that we're still looking for a limit as x goes to infinity. So I'm going to rewrite my work where we are, limit as x goes to infinity. But now I'm working with this new expression, 8x over the square root of x squared plus 8x plus x. All right, and now I'm going to erase what I have here. Now you can use your pre-calculus skills for finding a horizontal asymptote, for finding the limit at infinity. I'm going to work this using the strategy that we used in class. And what we did in class is that we divided each term by x to the highest power that we see in the denominator. So if I look at my denominator, I see that I've got an x squared here, which that seems to be the highest power, but notice that it's being square rooted. And so the square root of x squared is actually just x. And so x is my highest power in the denominator. I'm going to divide every term by x. So this is going to be equal to, still limit as x goes to infinity. In my numerator, I'm going to have 8x over x. In the denominator, over here at the end, I'm going to have x over x. I'm dividing by x. But under the square root, because I'm under the radical, I'm going to divide by x squared, because I'm dividing by the square root of x squared, which really is just x. So I'm going to divide x squared by x squared. I'm also going to divide the 8x by x squared, again because we're still under the radical. So now let's see how this simplifies out. In the numerator here, my x's, they cancel out, and I'm just left with 8 over, in the denominator, the x squareds cancel out, and so I have 1. In the next term, 8x over x squared, that x cancels out the squared, so it leaves me with 8 over x. So plus 8 over x. And then outside of the radical, x over x, those cancel out, and I have plus 1. Now remember, I'm thinking about this as x goes to infinity. So I have this expression here, 8 over x. Well, if my denominator x is going to infinity, if my denominator is getting infinitely large, that means that my fraction is getting smaller and smaller and smaller, and it is going toward 0. So that zeroes out that term, and what I'm left with is 8 over the square root of 1 plus 1, which is 8 over 2, or 4. And the correct answer is C, 4. All right, let's look at the next question. Pretty similar to what we just did, except that it's much easier because it's just the latter part of what we just did. Here we're looking for the limit as x goes to negative infinity. Now that piece is really important, the fact that my x's are negative. I'm going to use the same strategy here that I used in the last question, where I'm going to divide every term by the highest power of x, x to the highest power that I see in the denominator. And in this case, that's x squared, but it is square rooted. It's the square root of x squared. And so really what I'm doing is dividing by x. And so I've got x over the square root of x squared over x squared, dividing by x squared down here because it's under the square root, plus 1 over x squared. Now, what's tricky about this question is that my x is going to negative infinity. And so when I divided by x in the numerator, what I was really doing, or what I should have written, is that we're dividing by a negative x. Let's think about this. The highest power of x that I have in the denominator is that x squared, but it's under the square root. And so what we're doing here is we're dividing everything by the square root of x squared, because that's the highest exponent on x that I have in the denominator. But keeping in mind that in this scenario, x is going to negative infinity. And so when I take the square root of x squared, remember that when we square root something, it could be positive or it could be negative x. And in this case, since x is going to negative infinity, we're choosing the negative x. And so when I divided by x in the numerator, I really should have been dividing by negative x. Now in the denominator, we're still dividing by x squared under that square root, so I'm squaring the negative x's, which is turning them into positives. But in the numerator, it's the square root of x, and that x should be negative. So now that I've taken care of that, Let's simplify. In the numerator, my x's cancel out. And so I'm left with, my numerator, I'm left with -1. In the denominator, x squared over x squared, those cancel out. So I've got the square root of 1 plus 1 over x squared, which if x is going to -infinity, my denominator is getting infinitely large, which means my fraction is going to 0. And so really, I just have, whoops, not 1 plus 1, 1 plus 0. And so -1 over the square root of 1 is -1. And -1 is our answer. All right, I think this is the last question here for this video. This time we've got a table of values given to us. Suppose that f and g are continuous functions for all real numbers with values given in the table. And then they're defining a new function here. Let h of x equal f of g of x plus 4. So we've got a composite function, f of g of x plus 4. Which of the following statements are true? And the first statement says h of 1 is equal to 24. Well, I'm going to use this definition of h of 1. I'm sorry, that's my dog again there. H of 1 is going to be equal to f of g of 1. I apologize for Barkley. He doesn't understand what it means to be quiet while I'm making videos. All right, f of g of 1 plus 4. So now the values for this, to figure out what this is equal to, I'm going to get values from the table. So I'm starting out first of all here at g of 1. If I go up here and look at the table, whoops, sorry about that extra mark there. G of 1, well here's x equal to 1 right here. G of 1 is equal to 4. So I'm going to plug that in. So now I've got f of 4, still plus 4 out here. So now to find f of 4, I need to go back up to the table again. So I'm going to go back up here. Let me erase the marks that I made. Now I'm looking at an x value of 4, and f of 4, that corresponds to 20. So I'm going to change f of 4 to 20 plus 4, and that does indeed equal 24. So my first statement here is true. All right, the next statement, a number c exists with c between 3 and 4 such that h of c equals 13. Now hopefully you recognize that statement as the intermediate value theorem, because we're just proving that a number exists. That's our existence theorem, and I want to know that somewhere on the interval 3 to 4 that the value of h is equal to 13. So here's what we need to do. We need to find h of 3, and then we're going to find h of 4. So h of 3 is f of g of 3 plus 4. So I need to start out by finding g of 3. Let's go back up here to my table. If I look at 3 right here, g of 3 is 3. So I'm going to change g of 3 to 3. And we're still adding 4. Now I need to find a value for f of 3. So I've already got the 3 circled there. The f value at 3 is 15. So if I plug in 15 for f of 3 plus 4, that equals 19. All right, now let's do f of 4. I mean, sorry, not f of 4, h of 4. So for h of 4, f of g of 4 plus 4. So first thing I need to do is find g of 4. That's what's on the inside. So I'm going to go look at my table. G of 4, here's 4. The g value is 1. So this is equal to f of 1 plus 4. Now I need to find that value for f of 1. And here's my 1 value. F of 1 is 8. So if I plug in 8 plus 4, that is equal to 12. So notice my endpoint values here, I ended up with 12 and 19. And does that mean that h of c has to equal 13 somewhere in between those two numbers? Yes, it does. The thing that we need to confirm, let me highlight that we said originally in the problem that f and g are continuous. Remember, in order to apply the intermediate value theorem, I have to have a continuous function. And if f and g are continuous functions, then h of x has to be continuous as well. And since 13 is between 12 and 19, then that statement is true. Finally, the last one, does h of 2 equal 28? So I'm going to erase some of this stuff down here so I have a little more room to work. H of 2 equal to 28. Let's see. So h of 2 would be equal to f of g of 2 plus 4. So again, I need to start out by finding g of 2. If I go up here to my table, g of 2, here's the 2, the g value is 2. So now I have f of 2 plus 4. I'm going to go back to my table and find a value for f of 2. And that's going to be 12. And so I get 12 plus 4, which equals 16. And that is not equal to 28. And so that statement, our last statement there, is false. And so the question asks us which ones are true. So the true ones would be answer question statements 1 and 2, answer A.